All right. So we're going to continue on discussing Friedel alkylation. And while I'm kind of sketching this stuff up here, apologies if you guys have been getting some weird notifications through the Microsoft Teams app there. I was trying to find a way to link my notes directly into the app using OneNote, but it just well, I'm recording this, so I got to be careful of voicing my direct opinion on things. But anyway, here we are. So, right when we're talking about Fieldcraft's alkylation, right, we're figuring out ways to directly add alkyl chains directly onto the ring. We use some kind of alkyl halide and a Lewis acid to generate a cation, right? And that cation, right, was then attacked by one of the pi bonds within the ring, and we reformed the ring at the end there, right? And so the bad news, so to speak, right, was that when we generate a carbocation, we have to pay attention to rearrangements and shifts and all that kind of stuff, right? The good news is that if we can generate a carbocation, we can generate a carbocation, right? And that can be used to, and the ring can attack that. So the point being this: how many different ways do we know about how to generate carbocations? And the answer is, well, we've been dealing with them for quite a while at this point, right? So there's quite a few different methods that we have of doing this, okay? So let's see if we can kind of recall something that we can think about here, right? Right, and hopefully it'll become evident as to why this would be important or why necessary, right? This kind of stuff. So if I take my good old buddy T-butanol, okay, and I put in the presence of a pretty strong acid, right? Typically a nice, highly oxidized acid. And we can talk a little bit later, if you guys want to come by office hours, we can talk about why we choose these particular acids, right? We will end up getting this compound here, right? And this really shouldn't be too much of a surprise, right? We have an acid, we have an alcohol. We know that we're going to protonate the alcohol. We end up generating water as a leaving group, right? And so we can stabilize a tertiary, right? We can stabilize a tertiary cation, and that cation can then be added to the ring, right? And so here's, right, let's go through our quick steps here then. I'm just going to abbreviate this here as H plus, right? We'll skip drawing out the Lewis structure for phosphoric acid. That's okay. All right, anyway, here we are, right? Okay, protonate. All right. This can leave. Right? So generating, right? This is all generating the electrophile here in the top step, right? Now, I really should be careful when I'm doing this, and I should have been doing it all along, right? This is an equilibrium here, right? We do generate that cation, and then the water can come back in and then leave and all this kind of stuff, right? But, we're generating the electrophile is what it is, okay? And then, right, by the time I finish drawing this out and speaking it, you guys have probably finished it on your end also. Whoops. Right, I see this. Right, here's step 2, attack by the ring. And then step 3, something comes in and grabs that. So some kind of base, right? Some kind of base comes in and grabs that and reforms the ring, okay? What is that base? It could be the conjugate base of phosphoric acid. It could be water. It could even, it could be more of the alcohol, right? So a couple of different things can come in, right? So sometimes, you know what? Let me change this to purple here, right? Generic base, okay? So if you see this B minus thing here, right? Well, if it's on your report card, then you know what it means. But if you see a B minus here in organic chemistry, right, then you guys know it's just some kind of generic base. Does it matter what's coming in to deprotonate? No, right? It doesn't matter. It could be the alcohol, it could be the conjugate base of the acid. It could be some water, maybe another ring. You know, there's a lot of stuff in solution here, right? So don't worry about that, right? Some generic base is coming in to grab this, okay? This should look identical, right? Let me scroll up here for just a second, right? Where was it? Right here, right? So this is, you know, what we're just looking at there, right? It's identical to what we saw there, right? In the yellow, we generate the electrophile. In the green, the ring attacks, and in the black, right, it gets reformed. Right, so if I am continuing on with the colors, yellow, right, green, right, and then black right here, right? Fantastic. Cool, so there it is, right? Nothing too unexpected with that. Phosphoric acid's pretty good. We can also use this guy here, HClO4 perchloric acid. We don't really talk about perchloric acid too much. We don't really use it in the lab too much anymore. It's a really, really powerful acid. It tends to want to oxidize everything, and which, you know, can be useful in some cases. But anyway, some of these heavily oxidized strong acids can be used in this case to generate the cation, and then we can use alcohols to as starting materials to add to the ring. Okay. All right. Let's. I'm trying to find a good color here. Let's continue thinking. Okay. So let's say I have Mr. Alkene. Okay. And Mr. Alkene is having a good day, and Mr. Acid comes along, right? And then we end up getting this. Say, oh, great, cool, fine, right? Now I can use this, right? Right? Now I can use this, right? Plus some aluminum chloride, right? And we can do our Friedel Crafts alkylation with that, right? That's fine, right? You can do that. That's nothing wrong with it, okay? But, right? But you should go, right? What's the mechanism, right? What's the mechanism to go from here to here? That's probably one of the first mechanisms we learned, right? And if you don't know it at this point, then, well, well, you guys know it, all right? So anyway, right? We're just doing a simple addition mechanism to an alkene. What is the intermediate, right? Okay, well, we got a Bronsted acid. Typically with Bronsted acids, we generate cations, so we know that there's a cation intermediate. And so I think, if you guys are following along, then you know exactly where this is going, okay? This is another example where you have a mechanism, right? We have another example of a mechanism where we are generating a cation along the way. And so if we can exploit that cation, we can then add this directly to the ring itself. Except we can't really use HCl, right? There's a couple reasons for it, and again, it's a little bit outside the scope of what I want to talk about for this course, right? If we ever end up teaching advanced organic chemistry, I'd be happy to go back and kind of poke at some of these details. But for our purposes, HCl wouldn't really be a good choice in here, okay? We're going to use a couple of special acids, right? And that sounds kind of weird. But it's just, I'll give you guys a name here in a second, right? So what we want to do is if we start with an alkene, right, we want to use something called triflic acid. All right. Triflic acid, or, okay, we want to use this guy here. Okay. So triflic acid, or HUFSBUF, okay? I'm just kidding. That's hydrofluoric acid, or HF SBF5 adduct, okay? So SB is antimony, right? So we have a hydrogen fluoride antimony pentafluoride, right? Or antimony 5-fluoride adduct. This is a weird beast to be sure, okay? You might see this written as this, okay? HSBF6. Well, gee, why didn't you just write like that to begin with? Well, again, okay? Either way is fine. We're intending the same thing, okay? But there is a technical difference in between the two, although for us it doesn't really matter. Okay, who cares, right? Anyway, so triflic acid, or this antimony adduct there. Oh, yeah, so what is triflic acid? So triflic acid is a shorthand for trifluoromethane sulfonic acid. Trifluoromethane sulfonic acid. Okay, so trifluoromethane sulfonic acid. Okay, triflic acid. And now immediately you should go, wait a minute, we've actually seen that before. Yes, you have. Okay, way back in OChem 1, we've actually seen triflates. Okay, remember 8X, right? So if we have triflic acid, it turns into a triflate anion. Okay, so we have triflates. Okay, and triflic acid. These are, at the end of the day, right? At the end of the day, these are two extremely powerful acids, especially that antimony one, right? That antimony one is classified as a superacid. I forget the exact definition right now. I should pause this and look it up or whatever it might be, right? I believe the definition comes from its ability to protonate carbons. There's some metric for it, and I do apologize. I don't know it off the top of my head. I'll look it up at some point, and maybe in the next video I'll add some clarification for that. But anyway, there are multiple versions of superacids. And so technically speaking, we can use any of those here. Just as a quick thought, right, or as a quick, hey, that's kind of cool, there are certain superacids which can protonate a methane. So we could make CH5+, right? So that should kind of give you an idea of how powerful some acids can be, right? Now, it should also, right, go without saying that if we have a really powerful acid that can protonate methane, right, it's going to protonate the crap out of everything, right? So anyway, the point being here is that these are extremely powerful acids, and if I'm an extremely powerful acid, I make what? Aha! I heard the call through the empty campus, right? If I make a powerful acid, I make an extremely weak base. And that's the whole point. We need a weak base that's not going to coordinate back to our cation, and then it's going to go through and do our thing, right? So these are powerful acids. Let's just abbreviate these as H pluses, right? And then maybe you guys can see where the mechanism is already going to go for this. Remember step 1, right? Step 1, generate our cation. So we grab Mr. Alkene. Okay, Mr. Alkene is going to react with acid, right? Just for emphasis sake, right? We do a Markovnikov addition. I'm just going to put that there. There's our cation, and dot, 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 right? See if you guys can figure out the rest of what's going to happen here. The answer is it's going to look like this, right? So, oh look, right, there's our cation that we formed. The ring's going to attack it. Some generic base is going to come in, blah, 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 blah. Okay? So I think you guys get the point here, right? So we can use alkenes to attach to the ring if we have a powerful acid around. Do you guys see the problem here, though? Right? I talked about it, right? There's a problem here, and there's a problem here. It's useful because you say, hey, cool, I can make an alcohol. We put a powerful acid around. We can add that, okay? Hey, cool, I can make an alkene. We put a powerful acid around. I can add that to the ring. How selective do you think these acids are going to be? Well, the answer is they're not, right? They're really not going to be all that selective, right? And that's part of the problem that we have here, okay? And so we're going to have to take that into account for what we want to do, all right? So, yes, this is useful because we can add different functional groups, but, right, the utility in this case is a little bit downplayed by the fact that we have to have these really, really powerful acids that are around there. But, you know, to be honest, right, is that really that big of a deal? Does it really matter all that much? You know, it depends on what you want to make, right? It depends on what you want to make in this case, right? That would be my argument with this. All right. So let's see, how long have we been recording here now? 14 minutes. I think that's kind of a good pausing point for just a minute. All right. So I'm going to pause for just a second. I got to take care of something. I'll be right back and we'll finish up this video. Okay. All right, so let's do one last reaction here, and then we'll lead into the next topic, and it'll, kind of, this will kind of tie together here. So one functional group that we haven't talked about too much, wow, that's not an arrow at all, is a sulfate group, or a sulfonic acid group here. But if we do this, so if I take SO3 and I put it into H2SO4, what we end up making is this here, okay? Wow. Now, what in the world is this? Okay, so let's break this down just a little bit. This is what's known as fuming sulfuric acid. So the way they make sulfuric acid is they basically burn sulfur. Okay, so they get these, a mixture of sulfur oxides, SO2. They keep, oxidizing that. It turns into SO3, and then they bubble SO3, right? So SO3 plus H2O, right, makes, well, here, let me, no, that's okay. I don't need to color code this. I think you guys see where this is going, right? SO3 plus H2O makes H2SO4. Got it? So they basically bubble that through water, and it turns into sulfuric acid is what it is. And what you can do at this point is, of course, it's going to reach a saturation point with SO3. But if you just keep bubbling that stuff through there, right, you make what's known as fuming sulfuric acid. Maybe, for non-scientific terms, we should just call it really strong sulfuric acid. Okay. But anyway, so SO3, right? SO3 has a couple different resonance forms, right? So there's the Lewis structure, right? We can see this form, right? And then, obviously, we could draw the other resonance structures with this also, yada, yada, yada. But anyway, this is, right, here you guys can see what's going on. Right, aha, we've generated a cation, right? And the aromatic ring will attack that cation. It will add the SO3 group. And since we're under acidic conditions, it will turn it into an SO3H group there, right? So we can add that sulfate group, right, the protonated sulfate group directly to the ring. Cool. Who cares? Okay, well, what's useful about this, what's interesting, is if I then take this and I put it in with some dilute sulfuric acid. My product is this. Okay, so basically what we're saying is that this is a reversible reaction. And if you go through and you think about this, that kind of makes sense, right? Because SO3, right? SO3 here, this is a gas. So, we have to bubble this through the sulfuric acid there, and it fumes out, all this kind of stuff. And so if I put this under different conditions with dilute sulfuric acid, we're going to essentially reverse this reaction, right? So you can think about this, and I'm playing a little bit of some games here, right? So pardon me for a minute. Right? We can basically think of this as like reversing the equilibrium, right? We're turning that SO3H group back into SO3 gas, and that's bubbling out, okay? Now, but here's the important part. What does this look like to you, right? So we have a reaction that's easily reversible. So this is almost like a protecting group. And you're like, well, who cares? What are we doing? Protecting a hydrogen, right? Right, because there's basically a hydrogen there, right? And we come back and there's a hydrogen back there. Well, it's going to be important in just a minute, right? We don't so much call this as a protecting group for aromatic rings. We can call this a blocking group. All right? A blocking group. And we'll talk about why that's important, what the point is, and why do we need it, yada, 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 in just a little bit, okay? But we can add these We can add these sulfate groups to there, right? We can do this sulfonation reaction, and then we can desulfonate, right, by just putting it in dilute sulfuric acid. Okay, there are different there are different blocking groups that can be used, but you know this will you know what? Let's just use this one here, right? So this will be fine for what we need to do. Okay, but that's the end of this. In the next video, we're going to be getting into a couple of new reactions, right? But we're going to get into the idea of what happens once we add a functional group, right? So what, we add a sulfonate group, right? So what, we add an alkyl group. What happens once we add, you know, a halide? What happens once we do a nitration, right? What happens as we go through and do all these different reactions and mechanisms that we've been learning so far? How does that impact the ring, right? So that's what we're going to go to next. So I'll see you guys in the next video.